Thanks for joining me today. The focus of this webinar is going to be PCI Express 6.0 physical layer characterization, focused on PAM4 signaling at 64 gigatransfers per second. My name is David Bouse, and I'm the principal technology lead from Tektronix, where I focus on PCI Express specifically. I lead engineering teams to develop solutions around the latest speeds and features within PCI Express, and also represent Tektronix within the PCI SIG and adjacent bodies as well. So let's start today by looking at the evolution of PCI Express. So the 6.0 spec was released this year, so in January of 2022. And that's the base specification. And this is the document that describes all layers of the technology at a chip level. But today we'll focus specifically on the physical layers. And even within there, we'll focus on the electrical aspects of the physical layer. There's also the logical section as well. So the timing of this release is right along reaching critical mass for 5G technology and bandwidth needs associated with that. In addition, we're seeing quite a bit of adoption in the space of high performance computing and AI applications, all of which are needing increasing bandwidths. And you can see what bandwidths get delivered for this latest speed at 64 gigatransfers per second. The table on the right, you can see the bit rate per lane, link bandwidth, lane bandwidth, and also a by 16 bidirectional bandwidth as well. And you can see that Gen 6 has now delivered 256 gigabytes per second for that by 16 bidirectional bandwidth, which is pretty significant and exciting new inflection point for this technology. So PCI Express has trended towards a doubling of the bandwidth every 3 years. You can see that in the table at the left. Of course, there's been some pull in and push out, as different factors have impacted the schedule. But generally speaking, that has been achieved as we've gone from PCI Express 1 to 2 to 3, all the way up to Gen 6. Some of the key pieces that we focused on for Gen 6 were, increasing the bandwidth while maintaining a low latency, right? So PCI Express technology requires that very low latency as we're talking about CPUs talking to memory, CPUs talking to accelerators, and so forth. And you have to have that low latency to run these applications and move data from these compute nodes. Also backwards compatibility, right? So we've been focused on ensuring that the same connector supports latest data rate and also is backwards compatible to the previous rates as well, and that's been maintained now for Gen 6. So this table shows going from PCI Express 4.0 to 5.0 and now to 6.0, and some of the key electrical parameters that have moved during that transition and how they've evolved. So you can see we've gone from 16 gigatransfers per second to 32 to 64 now for Gen 6. And this is the first time we've gone to PAM4 multi-level signaling, right? So all of the previous rates have been NRZ 2 levels. Now we have 4 levels of signal, and that allows us to get 2 bits of data within a single unit interval or UI. The spec doesn't explicitly define a full channel loss, but it's somewhat indirectly defined in a couple of ways. First, you can see in the table, what our add-in card or endpoint loss is, and that's gone from 8 dB to 9.5 to 8.5 at the respective Nyquist, and you can see that static Nyquist as we've gone from Gen 5 to Gen 6. So that's one piece. That's a loss for the endpoint or the card. And then you can also see it's bounded by how much loss we use to test the receiver. And you can see a range, because that's actually one of the knobs that we use for calibrating the stress signal for testing receivers, which we'll talk about a little bit more. That was 27 to 30 for Gen 4, 34 to 37 for Gen 5, and 30 to 33 for Gen 6. You can also see the evolution of receiver equalization in terms of CTLE, adding more poles and more zeros. We're at 6 poles and 3 zeros now for Gen 6. More taps in the DFE equalizer, 2 to 3 to 16. And you can see the target eye width and target eye height that we calibrate to for receiver testing. We're now to 3.125 picoseconds and 6 millivolts for Gen 6. And since we actually have 3 eye diagrams, since we're dealing with a multi-level PAM4 signal, we focus on the top eye. Lane margining has continued to evolve. It was initially introduced for Gen 4, timing only, now required for timing and voltage, both for Gen 5 and Gen 6. Quite a bit of reduction on the allowed jitter from ref clock. We're now down to less than 100 femtoseconds of jitter allowed after the appropriate filtering has been applied. And you can see the real-time oscilloscope bandwidth requirements. 50 gigahertz is that requirement for Gen 6. So not only have we seen growth in the traditional PCI Express market, but we've also seen alternate protocols starting to be pretty prevalent. And one in particular is Compute Express Link, or CXL. We consider this an alternate mode. So it actually uses the physical layer of the PCI Express specification, but then it introduces a new layer of protocol on top of that that's more tailored to the types of applications we see running in the data center today. And this is really a response to those architectural needs to very quickly move data across the compute network, increase efficiency, focus on power, and support larger and more diverse applications in that space. And it really provides a memory expansion. So, it is a cache coherent memory protocol that allows that memory to be accessed by multiple CPUs and accelerators. And new trends that we're seeing with the release of CXL 3.0 that happened Q3 of this year, so just recently, is a move towards more of a pooling of memory out of the chassis that can be shared across these compute nodes. The interesting thing about CXL is it is form factor agnostic. So we'll see with time how we converge on certain form factors for certain applications. But we're seeing today an acceptance of CHEM form factor M.2, U.2, U.3, EDSFF, OCP NIC 3.0, and also emerging cable form factors as well. Within the PCI SIG, there's now a active work group that's developing standardization around PCI Express cables. So that's linked to a lot of the work that's happening in CXL and also future work that's happening within automotive and adoption of PCI Express in that space as well. So now I'm going to get a little bit more into the physical layer testing specifically, go into a bit more detail and talk about characterization of transmitters and receivers at this new speed of 64 gigatransfers per second. So first I want to look at, how do we access the transmitter and the receiver to do these tests at a base spec level? So you can think of this as silicon level verification, where we have a test chip that's typically laid out on an evaluation board. And there's kind of two main ways this can be done. So if the ref clock is not internal or not embedded to the package, then what we do is we provide a very low jitter clock source to the SerDes. And that allows us to really characterize the intrinsic jitter because we have that low jitter source that we can introduce. And the alternative path is, if that ref clock is embedded within the package, then there's a requirement to actually output that clock. And then you can use that clock to do what we call more of an embedded mode. So you can account for any jitter on that ref clock since you have access and actually remove that so you can get closer to that intrinsic value. For receiver testing, we actually want to capture the impact of that breakout of the data. So we also introduce a replica channel. And this allows us to have in the path for receiver testing, what that element would actually be getting into the actual package itself. So we can include that when we calibrate our stress die. So this is kind of the access methods that we use for testing transmit and receive. Now let's start with transmit and talk a little bit more about what's new for Gen 6. So we've introduced a second precursor on the transmitter for Gen 6. So we now have two precursors and one postcursor. We also call that de-emphasis for PCI Express. We have the traditional presets. These are predefined values for the coefficients. However, they've been redefined for Gen 6. We had the opportunity to do this since we have the second precursor for the first time. And so we've defined them in a more useful way. So for Gen 6, instead of P, we're using the letter Q. So you can see in the table, we have Q0 through Q10. And these presets are actually more tailored to the real channels we'll see and optimized for those channels. So you're going to see, more occurrences of those being used during training of the receiver actually requesting these. And you can see three that have been marked with a star here. And those are specifically optimal for receiver testing. So this is, worst case channel, worst case stress. We'll use these for stress die calibration when we're developing that signal to test the receiver. Also, new methodologies for measuring the transmitter and how well it meets the tolerances for the two precursors and the postcursor, what we call the AC fit method. So that's something to be aware of. It was first introduced in Gen 5, but that's been expanded for Gen 6 as well. So a couple new measurements that we haven't seen before in the PCI Express space, and some of these have been adopted from Ethernet, as Ethernet has gone to PAM4 before PCI Express. So the first one I want to talk about is the signal to noise distortion ratio. The acronym for that is SNRR. And you can think of this as a more accurate signal to noise ratio, where not only does it take into account the noise, but it also takes into account other non-linearities that are not compensable by the receiver. So that's our sigma E term. So that's the new piece. And what it is, we're performing clock recovery. We're coming up with the averaged waveform that we capture. And then we're comparing that with a step response recreation of the signal. And any deltas within there become our error term. And that error term is what we see as something that's not equalizable by the receiver. And so it's a penalty. And therefore we count that in the denominator with the noise as well. So this is something to look forward to as we move to Gen 6. And more of a focus on the vertical impairments as we have 1/3 of the eye height as we've gone to PAM4. So this is a continuation for measurements we've seen previously, uncorrelated jitter and pulse width jitter. What's new here is the method that we use for doing these measurements. And a couple things. So first, the pattern. We have new test patterns that have been defined for Gen 6, a new compliance pattern for doing the uncorrelated jitter, and a 0-3-0-3 high-low pattern for pulse width jitter. Some similarities between the two. We have a scope bandwidth of 50 gigahertz. We have introduced for the first time a fourth order BT filter that we apply to the waveform before we start running through the algorithm to compute the jitter. And we're allowing, again, CTLE from 5 to 15 dB to remove the impact of that breakout that we saw earlier as we're getting access to the signals that are on a test chip on an evaluation board and have to be cabled up to a real-time scope. And then the very new part here is capturing the instrument noise. In this case, it'd be the real-time scope noise and compensating for that, which we're doing both for the uncorrelated jitter and also for the pulse width jitter too. So a few things to be aware of, a little bit more complexity, but it comes with the benefit of more accuracy, which we dearly need as we have a reduction in our signal with PAM4. So next, let's look a little bit at the receiver. So what we've seen, the delta from Gen 5 to Gen 6 is, we now have a CTLE with 6 poles and 3 zeros, and our DC gain ranges from -5 dB to -15 dB in 1 dB step sizes. In terms of our decision feedback equalization, or DFE, we have 16 taps now, so that's an increase. And new constraints on those DFE taps that were developed empirically. And really the focus here has been, how do we define a relationship between those taps which doesn't result in burst type errors? And a burst type error is a propagating error that occurs when you have, a high toggle area within the signal. You get an error and that propagates down the bit stream. So it's aimed at minimizing that as much as possible, so we can, not have errors in time that are not correctable with our correction techniques. We have the traditional correction techniques, CRC, replay, but we also have a low latency FEC or FEC, people call it now as well. And because of that, we're allowed to focus our DER at E⁻⁶ instead of E⁻12, which we've done historically, which is one of the key components that allowed us to get to PAM4 signaling. So here's some of the challenges around testing the receiver. And we're really just, as an industry, starting to get into this. There's been quite a bit of work around developing the stress-dized signal that's delivered to the receiver. That receiver gets put into a loopback mode, so it transmits back out the bit stream after it's digitized, and then we can do a comparison and check for bit errors. And a lot of the work around that calibration procedure has been done. It was part of the pathfinding for the last few years as we've been developing this base spec for 6.0. And we're really just starting to get into testing the receivers and, member companies having silicon within their test chip and starting to look at this. So I'm sure there's challenges here that are listed and some that we've missed as we continue to evolve and understand this a little bit more. So to mention a few, accurate and repeatable stress die calibrations at 32 gigabaud PAM4, that gets us to the 64 gigatransfer per second. We now have to validate not only at this new speed, but also at the previous speeds, and we have 2 modulation schemes, NRZ and PAM4. So just a lot of testing that has to happen across all these different speeds, which we have to support to maintain the backwards compatibility. I've talked a little bit about instrument noise characterization and compensation. A lot of complexity around that, but thankfully T&M companies have done a lot of work around that to provide automated solutions to help with that. But something to be aware of and make sure you understand at the appropriate level how to incorporate that into your testing environment. And then as we go to actual testing, whether that be jitter tolerance testing, seeing how well the receivers can handle sinusoidal jitter at different frequencies and to what amplitude before taking on bit errors, or if it's a basic bit error rate test where we're just looking at, how many errors in time do we see with, this stress cocktail. And we're going to have to do that testing in the presence of spread spectrum clocking, or SSC, which is always an additional layer of difficulty. So something to be aware of as you move into the testing phase. Also, limited post-processing tools available today. So Tektronix has personally, taken that upon ourselves to develop our PAM4, what we call our PAM Jet tool, that allows you to do the DSP lifting. It's our compute engine around Gen 6 to help with that, as there's limited tools available. Also ensuring that we're capturing realistic crosstalk, as we're so sensitive now to any distortion in the vertical direction, whether that be noise, crosstalk. So we'll see, how that impacts our performance and our link stability. And then, also for receiver testing, we have to get that transmitted data back to the bit error rate tester, or the BERT, so we can do that comparison, and ensuring we're not introducing bit errors in that return path or that back channel is critical. So here's a view of the diagram showing all the different elements for calibrating the stress die signal at 64 gigabits. And I'll step through a couple of the key elements here. So starting on the left, is everything that's traditionally in the bit error rate tester, or BERT. So we have the ability to generate a 32 gigabaud PAM4 signal. We have the ability to make adjustments to the TX equalizer on what is it essentially the transmitter. We're treating the BERT as the transmitter, but what we call the PPG in that instrument. We have the ability to introduce jitter, random jitter, sinusoidal jitter. We have the ability to couple in noise, differential or common mode. Differential is essentially what we're using to capture our crosstalk term. And that gets us to our test points, TP1, which is the output of the BERT, and then TP3, which is after a cable. We try to use a very short, high bandwidth cable. And then from TP3 to TP2 is our physical channel. So we do actually use a physical channel here to try to model as closely as possible what we would see in a real link. So we have test fixtures, and then we have a replica channel. And that replica channel is capturing the impact of the breakout on the evaluation platform for the test chip, which we saw earlier. At TP2, that gets us to a real-time scope. And within the real-time scope, we're capturing either a step response if we're using a simulation method, or a waveform if we're using waveform-based method. And then we're applying receiver equalization, doing clock recovery. And then we're also embedding the package as well, whether that be root complex or a non-root complex for endpoint. And then ultimately our target is we need to calibrate the stress size signal to 6 millivolts and 3.125 picoseconds. There's some tolerance in the spec for that. And that's at a BER of e to the minus 6, since we are considering FEC now for this speed, and that will be the top I. So this is kind of the full channel case that we use for calibrating for receiver testing. And we have a couple knobs. The biggest knob we have is adjustments to the ISI, or the channel loss. And we have a range of 30 to 33 dB. And then we can also do some fine tuning using jitter, sinusoidal jitter, and differential mode interference, or what is our crosstalk term. So next we'll look at receiver jitter tolerance methodology, and this is, once we move from calibration to test, right? So now we take the BERT and we connect it to the DUT's receiver, and then we take the transmitter of the DUT and we connect it back up to the error detector. And for testing, we're actually using a modified compliance pattern. One key point is we have SSC disabled on the data signal. The TX equalization can be optimized for the receiver, so you don't have to use the same setting that you use for calibration. And we independently sweep the 33 kilohertz tone to capture the tolerance of SSC. So that's a key point, is that's swept, it's not turned on the data. So it's just one of our test frequencies. And for common clock testing, you can see one amplitude. And for SRIS, this is when you have a separate ref clock with independent SSC. You can see that larger amplitude that has to be tested of 15 nanoseconds. And then we have our jitter tolerance mask that ranges from 400 kilohertz to 100 megahertz. And then we have an additional tone that we introduce of 210 megahertz if our final SJ calibration value was greater than nominal or 0.05 UI. And then we're testing at a FBER target of E the minus 6. That's the first BER is what that stands for, without accounting for burst errors. So pretty similar in terms of testing to what we've seen for Gen 5, just some new challenges around getting that signal back to the error detector, testing with SSC, and now we're focused on a different BER. So this concludes the presentation portion. Thanks everyone for joining us today as we've talked about PCI Express, Gen 6, physical layer validation, and I look forward to taking your questions.